This is a recording of a webinar that took place on November 14, 2018. The video includes both the presentation and the question and answer session that followed.
Hello, today I'll be covering multi-level modeling for intensive longitudinal data. The format of this webinar is 1 hour of lecture and 1 hour of Q&A. I'm Michael Russell, Assistant Professor of Biobehavioral Health here at Penn State and an investigator at the Methodology Center. So what are the goals of the webinar today? Well, what I'd like to do is introduce, and I put introduce in quotes, multi-level modeling as a tool for analyzing intensive longitudinal data. And the introduce is in quotes because I know that many of you out there are familiar with multi-level modeling already. But I would like to sort of present multi-level modeling as a tool that is well designed to address some of the conceptual and statistical questions that we have for intensive longitudinal data. And so as part of that, I will be showing how to translate some key research questions in this space into models that can provide you with the answers you're seeking, and hopefully leave you with a sense of how to approach complex data such as intensive longitudinal data with multi-level modeling techniques. And I'll talk about very specific ways to do that. So first of all, let's talk about defining what intensive longitudinal data are. And there's no real hard and fast rule for what constitutes intensive longitudinal data, what actually makes longitudinal data intensive. One rule of thumb that's been offered is data with many measurements over time, more than usual, and perhaps a good rule of thumb would be more than 30 or so repeated measures per person. Typically in a panel data set where we follow people over years, we might have 5 to 10 perhaps, if we're going really intensive, observations per person. But an intensive longitudinal data set has substantially more than that. Another feature of intensive longitudinal data is that it's often sampled at irregular or subject-dependent time points. Now, we might be sampling people at 5 random points throughout their day, and the intervals between our assessments are random so that participants aren't expecting them. Or we might have subject-dependent assessments, such as we're interested in when participants engage in drinking. And when they do engage in drinking, we ask them to initiate surveys. So when we get those prompts will be dependent on when the participant drinks and if they drink. So we have issues there due to irregularity and subject dependence. So what kinds of collection techniques generate intensive longitudinal data? Well, there are quite a few, and they fall under the general realm of ambulatory assessment strategies. Things like daily diaries, where we assess a person once a day, perhaps at the end of the day, giving a retrospective report of their day, or perhaps at the beginning of the day, asking them about the day before. Ecological momentary assessments, also known as experience sampling methods, where we're asking people at random prompts throughout the day, multiple times a day, to sort of report on their current experiences and mood. And finally, wearable sensor streams, things like Fitbits that can get extremely intensive longitudinal data about step counts from moment to moment. There are ambulatory blood pressure monitors that can take blood pressure readings in a person's day-to-day life, and even wearable sensors that can detect alcohol intoxication through the skin in real time. The gist of the whole thing here is that the large number of observations that we get from these assessment strategies presents both a challenge and an opportunity for data analysis. And the challenge and the opportunity are the things that I'll be talking about today. Now, there are many ways to analyze this kind of data. There are many approaches you could take, but I'll be talking about multi-level modeling because I and others think that multi-level modeling suits intensive longitudinal data, or EMA, because it does the following things. It accounts for observations being clustered or nested within people. So 2 observations from the same person will be more highly similar than 2 observations across 2 different people, and we need a modeling strategy that takes that fact into account. Multi-level modeling allows us to estimate 2 types of relationships. So we can ask how people differ from themselves across time, from moment to moment. And Those are things that I'd call a within-person effect, as well as how people differ from each other on average. And those we'd refer to as between-person effects. Finally, it allows the individualization of regression estimates or regression effects via things called random intercepts, where we can see how the mean of an outcome across time varies across individuals, as well as random slopes. So we can see things like how a relationship between negative mood and craving is stronger for some individuals versus others. So there are many ways that we can address all of this. And 2 and 3 are the distinguishing features of multi-level modeling. These are the between and within person effects, and the individualization of estimates are really the forte of the multi-level modeling strategy. So let's talk a little bit more about between and within. So as I've hinted at, we have at least 2 levels of analysis in a multi-level model. We can have more than 2, but typically we split it into 2 types when we're dealing with multi-level models with intensive longitudinal data. We can ask between-person questions or who questions. Okay, and so here we're testing differences between people on average, and we can ask, are people who engage in a lot of smoking at greater risk for some sort of adverse outcome related to that, right? So the comparison there is who, a person against another, and we can do these sorts of comparisons through aggregates of the measures that we get in intensive longitudinal data over time. We can essentially see how people differ from each other on average in terms of severity of symptoms, amount, frequencies, etc. Within-person questions we might think of as being when questions. We want to compare people to themselves, for example, when they experience a stressor compared to themselves when they do not experience a stressor. And the repeated measures aspects allow us to sort of get within each person and see how a person changes relative to themselves across time or across situations with regard to some outcome or behavior. Now, the interesting thing here is that these 2 levels of analysis are completely independent, both conceptually and statistically. And although it might be tempting to make inferences across the levels, it's important that you understand that knowing something about one, knowing something about a between-person relationship, doesn't tell you anything about a within-person relationship, and vice versa. So it's important to consider both at the same time. So throughout this talk from here on, I'm going to use the example of mood and nicotine craving among smokers. And I'm going to be talking about a study that is, so it's a fake data set, but the data set was generated with this sort of study design in mind. Let's say that we invited 200 current smokers to complete mobile phone surveys about 5 times a day for 7 days. So at each assessment, let's pretend that we asked them about their nicotine craving, which varies on a scale from 0 to 10 at that moment, with 0 being low and 10 being high craving. We asked them about their negative affect through 3 items. We asked them about sadness, anxiety, and anger at that moment, and we take the average of those 3, and let's just arbitrarily say that's on a scale of 1 to 7. And then we're also diligent about our recording of time, so each prompt also has a timestamp associated with it, so we know the exact day, hour, and minute at which the reports were provided. Before we get into analysis, I just want to talk you through a little bit about data structure. So before we do an MLM, we need to have our data set up in what's called a person period or a long file. And a long file, I'll show you an example on the next slide, but a long file essentially has each row of your data set corresponding to an assessment period. So an assessment, one single repeated measure that you gave to that individual across a number of items. So that's on each row. And we have multiple rows for each person. Okay. So if we take a look at this long file here, we can take a look at the ID variable and see that person 4 has a number of rows, each one corresponding to a different assessment period. Okay, so here's person 4. And we can see that they have about 5 assessments on the first day, which is marked with the date, so that's March 3rd. And then we have the hour and minute at which they gave us the report, as well as their craving at that moment and their negative affect or negative mood at that moment. And we have repeated assessments for this individual. Now we can also look at participant 5 and we can see the same setup. So each person has multiple assessments associated with them. Okay, and once we have our data set input and structured the right way, we can start to think about what a between and within person difference might look like on an outcome. So here what I'm showing you is a panel plot where we have 8 participants, and each cell here, each panel, is a different participant and marked with the ID on the top. So that's participant 10, 11, 12, 13, etc. On the x-axis, we have the observation number. So this is just the count of the number of repeated assessments that they're getting. And so we can see what they reported for craving on the y-axis at observation 0 being sort of the first, observation 1, 2, 3, 4, 5. Okay, and so each individual data point that they provided on craving is noted with a blue dot. Okay, now you can take a look and see that the many blue dots for each person are giving us the repeated assessments that we're after. One thing that we can do is we can calculate the mean for each person, okay? And so that's represented by the red line. So that's just the average of all of the craving observations or craving reports for each individual. Okay, and so we can notice a few things here. The first thing we can notice is that for some individuals, this red line is higher than it is for others, right? So indicating that on average, they have higher craving than others. And we can see that when we compare somebody like participant 11 to participant 12, okay? Now we can also notice that people aren't just hovering around their average value in terms of craving. Their individual craving reports are scattered about their mean, okay? And we see that for each and every individual. Now I'm calling your attention to both of these parts because each one is sort of informative about between and within information. If we compare the levels of the red lines, then what we're looking at is a between person effect. We're trying to ask questions about who has higher levels of craving than others, and what actually might cause them to have higher levels of craving on average compared to another person. When we're looking at the scatter of the blue dots around the red line, we're trying to understand why a person has a higher level of craving than they normally do at that moment. So that would be a within person question, right? So why does participant 10 have a higher level of craving around observations 20, 30, etc., than they do typically, or than they do at previous time points? Okay, so this plot I find very helpful for visualizing what we mean by a between and within person effect. So our first question, before we get into modeling between and within person differences, we might just be interested in what's the variance at the between person level? How much do people differ from each other on average? And what's the variance at the within person level? How much do people differ from themselves on average? And we can start to answer those questions using something called an empty multi-level model. So this is our first model that we'll be talking about today. And all it's doing here is, so at level 1, we have a simple model that's what we might call an intercept-only model or an empty model. And we're saying that for each individual, so craving for time I and individual j, is a function of an intercept, which corresponds to that person's mean craving across all their observations, plus a residual, which corresponds to the difference between their craving at that moment and their average. Okay, so conceptually you can think of level 1 as running a different regression for each person, which in this case means we're just calculating a mean. Then at level 2, we can estimate how those means, how those intercepts differ between people. Okay, and so we can say that the mean of craving for person J is a function of the grand mean of craving in the sample, and that's the gamma 00 parameter, plus the deviation or the difference of their mean from the grand mean, which is represented by the U parameter. Okay? And if you are familiar with multiple regression, you might recognize the residual, the EIJ, as sort of the leftover variability that's unaccounted for in the model. Okay, so this is sort of the variability around each person's mean. And we can also talk about the U terms as being the variability across the means, right? So it's telling us something about the differences between the mean craving for person J and the mean craving for another person in the sample. And so the variance of the E terms gives us within person variance. The variance of the U terms gives us between person variance. Okay? And so combining across the two levels, we can get what's called the mixed model. Okay? And so this will look a lot more familiar to you if you're used to running multiple regressions, where you can see that all the terms can be written out on one line. Now I'm showing you this because this corresponds to what the mixed model in many statistical programs is actually going to estimate. It's going to estimate the grand mean, the between person variance, the variance of the U's, and the within person variance, and that's the variance of the E's. Okay, and so I'm showing you that on this slide here. So that gamma 0, 0 that I called the grand mean of craving, in multi-level modeling speak, we'd call that a fixed effect. Okay, so fixed effects generally refer to regression parameters, okay, that we're all used to seeing. So intercepts, slopes, relationships between variables. The model has two random effects, okay, and so the variance of these U terms is what we would call our random intercept, and that gives us the amount of between person variance. Random effects generally refer to the variances in your model. So fixed effects are referring to regression coefficients, essentially the model that predicts your mean. Random effects are referring to the variances in your model. And so the first variance we have is a between person variance. The second one is our residual variance, which in this case is our within person variance. And so if we run a model that's an empty multi-level model, this is the output that we would expect to see. So in our fixed effects portion of our output, we would see just an intercept, and this corresponds to the grand mean of craving across time. I'll interpret this a little more on the next slide, but for now we'll just be comfortable saying that's the grand mean of craving across all persons and all observations. And then if we go to the random effects portion of our output, which in SAS is called the covariance parameter estimates table, we'll see that we get a between person variance, which is marked by this UN11 here, covariance parameter. I'll talk a little more about what that means on a future slide. And then we also get the within person variance, which is marked with the residual. And so if we interpret these things a little bit more, what we see is that a fixed effect, the fixed intercept is a value of 5. Okay, now remember the scale for craving was from 0 to 10. And so the intercept in this case is telling us what's the mean of craving across all people and observations. And we get a value of about 5 midway through the scale. In the random effects table, we can ask the question of, do some people have higher mean craving levels than others? Okay, and so looking at the variance parameter that tells us about between person variance, we can see that we have a variance of about 7 across individuals. Okay, and that's difficult to interpret in and of itself, but one thing that we might do is take a look at the p-value associated with that. And that is telling us that the variance of mean craving levels is higher than we might expect from random chance alone, suggesting that people do in fact, on average, have higher mean craving levels than others. Some individuals do have higher craving levels than others, and those differences are greater than we would expect by random chance alone. We might also ask, does craving vary significantly from moment to moment within a person? And we can see that the residual value, the variance estimate there is about 3.91, and that is also significant. saying that there does appear to be meaningful fluctuation in craving from moment to moment within a person, beyond what we would expect by random chance alone. Now, once we have these variance parameters, we can think about describing the variability in our data a little bit more by calculating something called the intraclass correlation. And this is important in multi-level data sets because it's telling us something about the proportion of variance in the outcome that's at the between-person level versus the within-person level. You can also think of the intraclass correlation as a clustering coefficient. If you were to calculate correlations between all of the repeated observations and take the average of those correlations, you would get the intraclass correlation. And so it's calculated like this. You essentially take the between-person variance from that table that I showed you on the previous slide, and you put that in a numerator, and you divide it by the total variance, the between plus the within. So it's a proportion that goes from 0 to 1. Hopefully that's clear from this formula. Okay, so if we do that with our example here, we have our between-person variance and our within-person variance. If we plug that into our formula, you'll see that we get an ICC of about 0.6. This is a strong amount of clustering across time. Okay, so what this is telling us is that there's 64% of the variance in our craving outcome is at the between-person level. Okay, it's at those mean differences between individuals. If we take 1 minus the ICC, we can get the amount of variance that's within people. Okay, so about 36% of the variance is at the within-person level, and that's how people vary from themselves across time. Okay. Now, typically, this is a high level. This is a high ICC for a lot of variables that we're interested in EMA or ILD datasets. You'll often see ICCs of about 0.2 or 0.4, particularly for things like stress and mood. But craving tends to be a little bit more stable over time, which sort of produces this high ICC. Now that we know a little bit of about the variance at the between and the within person levels, we're going to go in and try to predict it. Okay, so let's think about negative mood as a predictor of craving. Okay, so we might be interested in that relationship, and if we really think about it, we could convince ourselves, I think rightly so, that the relationship might exist at two levels. At the between person level, we might think that people who show higher levels of negative mood, on average, will show higher levels of craving on average. Okay? At the within person level, we might expect that when a person's negative mood is higher than it is normally for them, their craving might also be higher than it is normally for them. Okay, so these are two different relationships that we might want to test. And so on prior slides, I was splitting up the variability in craving into the between and the within. And so I've just duplicated that output on the left-hand side of the slide here. But I'm also doing this for negative mood on the right-hand side. And you can see I calculate a negative mood mean across all people and observations of about 0.5. But then I also estimate the between and the within person variance using an empty model. And if I calculate the ICC for negative affect, I find an ICC of about 0.35. Okay, so that's telling me that 35% of the variance in negative affect is at the between person level. And it's also telling me that we, in both our independent and dependent variable, are seeing significant between and within person variance. And this is going to become important when we go to model the relationships at both levels. Okay, and we can confirm that with this plot here. You can see the between and within variability for negative affect. Some individuals have higher levels of negative affect than others, and you can see that's indicated by the red lines that indicate their means, and you can also see that people are scattered about their means, showing variability in these scores from moment to moment. Now, one thing that I want to point out here that can sometimes get lost is that the multi-level model does a good job of separating the between and within variability for the dependent variable. But a standard multi-level model does not do this for your independent variable. And we actually have to set up our independent variable so that we have a variable that is only the between-person variability, and then another one that's only the within-person variability, because the modeling won't automatically do it for us. Okay, and so we can achieve this through centering. Now, the idea of person mean centering, and if you are familiar with HLM to studying things like effects at the school level versus the classroom level, or student level versus classroom level, you might have called this group mean centering. But in the intensive longitudinal space, where we typically have many observations per person, we tend to call this person mean centering. And the idea is to disaggregate our predictor to have between and within person parts split into separate variables. And so we can think about negative affect at each time point, which is our predictor, as being a function of the mean for that person, so that's the NA bar for person J, plus the deviation of their current score from their mean at that time. Okay, and so the between part is captured by the mean for person J. The within part is captured by that difference between their score at that moment and their mean. Right? And so what we will do in order to calculate this is we will in our intensive longitudinal data set, we will calculate a variable for each person. That's the mean of our predictor. Okay, so that'll be the mean of negative affect for each person. And what that's going to capture is between person differences. It will only vary between people. It will not vary within a person, because it's their average across all observations. Then what we'll do is we'll take our person mean that we just created, and we will subtract it from our original negative affect score. And that will create those deviations of the negative affect at that moment from that person's mean. Okay? And what this is going to do is it's going to capture within person differences, because it will only vary within a person. Okay? By centering around each person's mean, we will functionally set their means to 0 on this variable. Okay? And so here's what your data set might look like. So I've got negative affect, and it's grand mean centered to start with. You don't have to start with it this way, but I typically do. So I'll grand mean center it, and then I'll calculate the mean of that variable for each person. So you can see for person 4, you have the mean of negative affect for that person. And then for person 5, you have the mean of negative affect for them. And you can see it never changes across observations because it's their average. And then for person 6, they have a different means, right? So the only differences you're seeing are across people here. Right? And each one has a different one. Then what we can do is, if we subtract our mean variable for each person from the original variable, we get a deviation score. And so I'm calling this negative affect centered within, CW. And that's telling us how much higher or lower in negative affect units this person is from their average at that moment. And so you can see that this varies within a person. Okay? What you can't see right away is that the average of this variable is going to be the same across all people. Okay, and I'll show you that. So if we take a look at our original variable, this is our original negative affect variable, you can see that the mean lines differ, right? So some people have higher mean levels than others. But after we subtract each person's mean from the data, you can see that it sets that mean to 0 for everybody. So the only variability we now have left over in the person mean centered variable is the variability of each observation around that person's mean. Okay, so this variable can only predict within person differences in the outcome. Okay, so if we relate this back to our who and when questions that we talked about earlier, when we model these two pieces, these are the types of questions we're going to be able to answer. So the person mean negative affect is going to be answering who questions. We're going to be able to ask, do smokers who have higher mean negative mood also have higher mean craving? The person mean centered is the within part, and this is going to answer our when question. do smokers experience higher craving when negative affect is high compared to themselves when negative affect is low? Okay. And one thing I want to point out, this sort of reinforces my point earlier. So the first thing is I started with a grand mean centered variable because I wanted the means of both of these variables, the between and the within parts, to be 0 across all observations. This will make the interpretation of our model a lot easier, and we'll talk about that. Okay. But what you'll also notice is that the between and within parts are perfectly uncorrelated, okay? And this sort of reinforces the point that I made earlier. Knowing something about a between-person relationship will tell you absolutely nothing about a within-person relationship, and vice versa, because the two variabilities are completely uncorrelated with each other. Okay. And so in essence, you can think about this as having residualized negative affect on its person-level means, if that helps you think about this. Okay, so now what we're going to do is we're going to elaborate our multi-level model by adding in predictors. So now at level 1, I've got a more complicated function, but you can think about this as a regression for each individual, where now we have an intercept plus an effective negative affect at that time point. Okay. And so this variable is our person mean centered variable, this negative affect with the curvy hat on top. 0 on that variable is typical negative affect for each person, and variation in that variable is going to predict within person changes in craving. Okay, and its coefficient that we're going to estimate is this gamma 1, 0. Negative affect J is the person mean, okay, and the negative affect straight bar on top, J is the person mean. 0 on that variable is the grand mean of negative affect. And variation in this variable is going to predict between person differences in craving from between person differences in negative affect. The coefficient that we estimate for that is this gamma 0, 1. Because essentially what we're doing here is we're doing a different regression for each individual. This isn't actually what the model does, but you can conceptually think about it this way. And then modeling the parameters that we get for each individual across individuals. So now we get a mean of craving for individual J when a person is at their typical level of negative affect. And that mean for that person is a function of the mean craving for the sample, that's the gamma 0, 0, plus the effect of their average negative mood. So if there's a positive relationship, their average craving will be higher if their average negative mood is also higher. We can also think of this relationship at the within person level between negative affect and craving as a random variable that differs between individuals. So gamma 1, 0 is telling us about the average within person relationship. Okay, and each person is allowed to have a different relationship, and that's captured by a difference in the slope term for that person, and that's the U1J. For some people that relationship will be higher than the average for the sample. For some it will be weaker or lower. Okay, and so the model is going to estimate all of these things. It's going to estimate this U0J term, which is the craving mean for each individual after we've accounted for their negative affect mean. This U1J is the association between negative affect and craving for person J. Okay, and both, we're going to calculate variances in both of them, and we're going to let them covary with each other. And then the EIJ term is the craving within level residual that we always interpret as sort of the leftover variability at the within person level after we've accounted for negative affect, which is our predictor at that time point. So let's look first at our fixed effects. Now remember, fixed effects are regression coefficients, and they're going to be giving us both between and within associations. So let's start by interpreting these. Now the intercept is telling us the mean craving. Okay, the intercept is giving us the predicted craving for a typical person, right? And so what I mean by typical person is a person who has an average mean level of negative affect on a typical moment, and that's an average negative affect moment for them. So Typical person, typical moment. What's the mean craving that we expect? We expect 5.07 on a scale of 0 to 10. The negative affect CB, and that's centered between, is giving us the between person effect. And that will tell us people who have higher mean negative affect have higher mean craving. And if we want to get more precise about that, a person's average craving is predicted to be 2.2 units higher for each unit increase in their average negative affect. Okay, and we have a standard error and a p-value associated with that, so we can talk about whether or not that effect is significant. And here we see it is. Now we can also talk about the within effect. Okay, and we can look at the negative affect CW, centered within, and that's saying when negative affect is 1 unit above a person's typical negative affect, their craving is 1.3 units above their own typical craving. Okay, so again, that's answering the when question. Now let's get to the random effects. Now this is where multi-level models can get complicated. So I'm going to talk you through this as clearly and slowly as I can. But you know, some of this, some of the nuances will also be addressed in the Q&A. But when we estimate multiple random effects in a model, we can ask SAS or any other statistical program to give us sort of a matrix of these random effects. And so if you think about a correlation matrix or a covariance matrix, this is exactly what SAS is giving you, but related to the random effects. Now the G matrix is the covariance matrix of our random effects. And so if you look at row 1, column 1, that's giving us, we interpreted this just like a covariance or a correlation matrix. Row 1, column 1 is giving us the variance of the intercept term. Row 2, column 2 is giving us the variance of the slope term, right? The variance of the relationship between negative affect and craving across people, right? So the diagonals of a covariance matrix are variances. And if we look in the off diagonal, we're getting the covariance between a person's mean level of craving and their craving negative affect relationship. And so SAS uses this matrix notation to give you the standard errors and the p-values associated with it in a separate table called covariance parameter estimates. And so if you sort of follow the matrix here, you can see row 1, column 1. Okay, so this is what's called an unstructured matrix. So SAS puts the UN in front of the matrix identifier after it. So unstructured matrix, row 1, column 1, gives us an estimate of 6.236, which you can see corresponds to the variance of the intercept. And that's how much craving levels on average differ between people. And we can see that there's a significant variance in the intercept. Row 2, column 2, I'm going to move down a couple of rows, is the variance of the slope. And that's asking that question of, is the relationship between negative affect and craving at the within person level stronger for some people than it is for others? And we can see that there's a significant variance estimate there. So we can conclude that in fact it is stronger for some individuals than it is for others. We also have a covariance between these two things, and the covariance is negative. Now in order to really interpret this, it helps to visualize the data. But so far what this is suggesting is that if you have a higher mean level, you have a weaker relationship between negative affect and craving. So for example, if your average is very high, this could be suggesting a ceiling effect. If your average is very high, if your craving level tends to be high across the entire day, it's unlikely that your negative mood is going to be bouncing your craving up as high as if your craving tends to be lower on average. That's probably what it's telling us, but we have to unpack it a little more to really know. Okay, and so what I've put here in the text is representations of what each of these things is talking about, right? So the UN11 is our random intercept and variance and mean craving levels between people. UN21 is the random covariance between mean craving level and that within negative affect slope. The UN22 is the random slope, and that's your variance in the strength of the negative affect and craving association. And the residual is that unexplained within person variance in craving. Now, if we were to estimate all of the individual relationships along with the average relationship in the sample, we could produce a plot like this. Okay, and so what you're seeing here is on the red line, we're getting the parameters that we got from our fixed effects. And so this is the average line. It's the average of the within-person relationships here. And so on the x-axis, you're seeing negative affect, person mean-centered. On the y-axis, you're seeing craving. And you can see, on average, craving is increasing on moments when a person's negative affect is higher than their typical. And it's decreasing when their negative affect is lower than their typical. But each of the individual blue lines represents the model estimated relationship for a single person. And so you can also see that some people are tending to have higher levels of craving on average, right? Their lines are placed higher on the y-axis than some, or than average. And you can also see that the slants of the lines are different. All these lines are not parallel. For some, the rate is increasing. It's increasing a lot faster, like for this individual who cuts across others. For some, it's increasing more slowly. Okay, so a line that doesn't increase very quickly might be this one. And we can map this visualization onto the parameters of our model. That gamma 0, 0 is giving us the mean of the intercepts, and that's the value of the red line when negative affect is 0. Gamma 1, 0 is giving the mean of the slopes, and that's the change in the red line as negative affect increases by 1. The variance of the intercepts can be captured as the differences in the values between blue lines when negative affect is 0. Technically it's going to be the average of the squared differences, right? But conceptually it's the differences of those things. The variance of the slopes is the differences in the slopes or the slants of the blue lines, like I was talking about earlier. Now, we talked about intercept and slope covariance. So what I wanted to do was sort of plot this out. So what you've got here is a plot where you have each person's slope, and so that's the craving negative affect association on the y-axis. How much craving is increasing within a person when negative affect increases by 1 unit. And so for some it's increasing 2 units, for some it's increasing 1, some fewer. And on the x-axis you have the person's craving mean, so just their average during typical moments. And what you can see is a scatter plot. Each point is the data for a specific person. It's the intersection of their slope and their intercept, right? Their craving negative affect association with their craving mean. And if we cut a line through those, you can see that there's a trend here. So the higher your average craving, the less steep your negative affect craving slope. Okay? Or the higher your craving mean, the less of an effect negative affect is having on your craving. Okay, and so if you put that in a correlation metric, it's about a negative 0.3 association between your mean and your craving negative affect association, and it's a significant relationship. Okay, this might suggest a ceiling effect, or for people who have high average craving, they can't really go as high as somebody who has low average craving on a high negative mood moment. Now we can also start to predict individual differences in the within-person relationship. In this model, we just said that they varied between people. Okay, so for some people the effect was stronger than for others. We can try to explain that effect. Now this can also be a little bit complicated, so I'll walk you through this as clearly as possible. But what I've done differently in this model is I've only added one thing. I've added the mean of negative affect as a predictor of the relationship between momentary negative affect and momentary craving. Okay? And so by doing this, I'm trying to answer this question of why do some people have stronger links between mood and craving than others? It could be that people who have more negative mood on average, people who are just grumpier on average, might be more reactive to moments of high negative mood. Okay, and so that's what we're going to be testing by adding a person's average negative mood as a predictor of that momentary relationship. between their current negative mood and their current craving. And so we're essentially taking the negative affect person mean as a predictor of the slope. Okay, and if we do the math, and don't let this be too intimidating here, but if we actually work the math out here, we can see something pretty clearly, and that's that our intercept function is the same as it was in the prior model. Okay, where we have the mean of craving for a typical person at a typical moment, plus the effect of their average mood on their craving mean, okay, and the leftover variability there. The intercept is that. So the slope term, though, is now a function of not only what your level of negative affect is at that moment, but what your average negative affect is. Okay, and so that gets expressed as an interaction between that person's average negative mood and their current negative mood. Okay, and so in the multi-level modeling world, we call that a cross-level interaction. It's an interaction between a between-person factor and a within-person factor. Right, and so if we try to interpret that, what you can see is that our main effects are the same, or approximately similar. Okay, so we're still seeing a significant within-person effect. We're still seeing a significant between-person effect. But we have no evidence that the within-person relationship differs based on your average level of negative mood. Okay, so and we can, if we do simple slopes and we sort of estimate, what's the within-person effect for a person that is sort of less grumpy, what's the within-person effect for a person that is more grumpy, we can see that they are significant within-person effects for both the non-grumpy and the grumpy individuals. But if we look at the interaction, that's testing the difference between high and low negative affect average, or high or low levels of average grumpiness, you could say. And that p-value there is not significant. So we're not finding a significant interaction effect. It doesn't appear that your average level of negative affect is predicting the effect of your current negative affect any differently than just sort of random variation. Now, there's of course many more things that I could cover. I hope that sort of gives you a flavor of the types of things that you can get after in a multi-level modeling framework with intensive longitudinal data. I just want to mention other kinds of models that you might consider. So far, all of our momentary within-person relationships were estimated relationships at the same time point. So they sort of function as correlations. It's sort of a really fancy correlation. Now, we might be interested in more predictive models. We might be interested in your negative affect at a couple of hours prior on your the effect of negative affect 2 hours ago on your craving now. And so we might create a lagged variable that tries to get at directionality. Does previous negative affect predict current craving? And we might think about autocorrelation of error. So I haven't gotten into this, but our residuals currently are assuming that observations closer together in time are not more similar than observations farther apart. And that might be an invalid assumption. It's one that we can test by adding time-related dependency across residuals. And I'll point you to some books that talk about that at the end of this talk. We might also think about 3-level or even 4-level clustering. A 3-level clustering model, though, might parse our data into moments within days and days within people. And this might be important if you're really interested in things like day-of-week effects, right? Maybe you think that there's random day-to-day variability, and that moments within days are more similar than moments across 2 days, even within the same person, and you want to model some of that variability. You could do that with a 3-level model where we sort of partition the variance into the within-day variance, the between-day variance, and then the between-person variance. Multi-level models have also come a long way with generalized versions. So there are, of course, logistic models for predicting binary outcomes. So you might predict events like, did this person smoke a cigarette or not? Did they engage in heavy drinking on that day versus did they not? You might also think about over-dispersed Poisson, where we're interested in a discrete count variable, and maybe that variable is zero inflated. Perhaps it's the number of drinks you had on a given day, where most days would be zero, but some days you have perhaps a moderate to large number of drinks. These modeling frameworks can account for these types of non-normally distributed variables. Finally, there are many models for time trends. You can think of time trends as capturing structured change in outcomes with time. It's sort of growth processes or decay processes, cyclical processes, things like that. So, time of day might be an important factor for craving. Maybe people's craving tends to be high when they first wake up, but lower throughout the day. Day of week might be important, particularly for things like drinking, where we would expect to see spikes in the amount of drinking on Fridays, Saturdays, and Sundays. And multi-level modeling can account for a variety of shapes. You can use polynomial trends where we have squared and cubed terms, splines, things like that. More complicated models, you might be interested in looking at time-varying effect modeling or similar models that really can kind of get after complexity in time trends, sometimes a little bit better than multi-level models can. Right, so the conclusions that I hope you're taking away today is that multi-level modeling is an extension of multiple regression, where we're essentially doing multiple regression but at two levels, partitioning variance in our predictors and outcomes in order to estimate between and within associations. The model, in doing so, is adjusting for the clustering of observations that are present in intensive longitudinal data, and allowing us to model a regression association for each person and understand how the regression parameters differ across individuals. We can test within-person relationships, and as I've said, examine between-person differences in those relationships. Okay. A number of multi-level modeling programs exist, so SAS-Proc Mixed is the one that I typically use, but Stata has XT-Mixed, also XTME Logit, XTME Poisson for non-normally distributed outcomes. SPSS has the mixed program. M+ has type equals 2-level random, and multi-level structural equation modeling is a very exciting thing where we can start thinking about latent variables and sort of partitioning measurement error out at both the between and within person levels. Of course, there's R, and then the old school hierarchical linear modeling package and MLWin. These are some books that are really helpful resources. I highly recommend Intensive Longitudinal Methods as an introductory guide. Gives you a good conceptual overview as well as examples and ways in which to write up your analyses. They have sample code on their website. It's a fantastic introduction. Multi-level analysis goes a little bit deeper into the some of the nuances. Applied longitudinal data analysis does a fantastic job as well. And the Handbook of Research Methods for Studying Daily Life does an excellent job, not just with the modeling of intensive longitudinal data, but with collection, things like calculating compliance, how compliant were your participants with the repeated measures, etc. And I'd also like to point out that there's an online course on the Center for Multi-Level Modeling at the University of Bristol. You can take this course for free online by following this link. Highly recommended. And finally, you can visit our Methodology Center page. Our ILD page has SAS code, examples, podcasts, and more, and it's at this website here. And if you're not already signed up for the Methodology Center e-news, please do so. Thank you very much.
Okay, first question. Mike, I know it's not a short answer, but could you talk briefly about how to incorporate time into the models?
Yes, I absolutely could. So there are many ways to do this. You could have, the first thing that we might do is think about the effect of time in a sort of systematic way. So when I was talking about at the end modeling time trends, and I mentioned diurnal cycles, we could specify a multi-level model. I'm going to use the board, I think, because I sort of like to write this stuff out. Hopefully people can see this.
Hold on a second. Can you stop screen sharing so that your video becomes the big things that people can see?
Stop share.
Yeah, there you go. That's right, better.
Good?
Yeah.
Okay, so you can see this, Aaron?
Yeah.
Okay.
Yeah.
So let's model time. Okay, so let's say we're interested, I'm going to stick with the craving example. So in our level 1 model, you might have craving, person I time t, and then we have an intercept, and then we could just do a linear effect of time. And so time could be hours of the day. Okay, and then at level 2, we could let everybody have an initial value. Let's say time is coded where 0 is the start of the day. Let's just say 0 is 8 a.m. for the sake of argument. And so the intercept for person I would be their predicted craving at 8 a.m. Okay? So we would have an average predicted craving at 8 a.m. plus a deviation for that person. So that person's average craving at 8 a.m. would be the mean plus their deviation. Then we would also have a time effect. So this is how much craving changes with each hour. Okay. And so for each hour, how much does craving change? And so this is the average within person change in craving with each hour, plus the deviation for person I. So for person I, their average change is gamma 10 plus u1i. And so this is a very simple model that will give us a prediction that looks like this. Okay, so if the slope is positive, for example, it'll just be a straight line. Okay. We could make this more complicated by adding squared terms. So if we added another parameter that was sort of beta 2i plus or times t squared, then we might predict craving to do some sort of curvilinear change like this. And we could elaborate this model more and more to get more and more complicated change functions. So that's one way we could incorporate time. Another way we could incorporate time is to think about past values of craving as predictors of future values of craving. Okay, so we could essentially set up a model where craving, and I'm just going to draw that model out conceptually, where craving at time t minus 1 is a predictor of craving at time t. And then we could also think about, well, how about negative affect at time t minus 1? So adjusting for the autocorrelation, we could start to build in predictions of one time point to another time point. Now this gets tricky in EMA because the timing of our effects is important, and we have to sort of think about how long should it take for negative affect to affect your craving? Does our design match the theoretical idea of how long it should take? Okay, but we could incorporate effects that way. We could also think about how the residuals are correlated across time. Okay, so the first way that I mentioned was sort of modeling time trends. The second way that I mentioned was thinking about auto-regression, right? Where one time point is predicting another time point, t minus 1 to t. We could also think about the fact, so in the models that I've run, when I showed you that residual term, there's a different residual term at each time point, but we make the assumption that if we look within a person, I'm setting this up to show you this. Okay, so if here's the residual term for person one, person one, person one, time two, time three, time four. And so this is the within person residual. If we sort of look at the correlation matrix of these, I'm putting ones on the diagonal. Our standard way of dealing with this is to assume that these are independent. Okay, so that the residual at time one is not correlated with the residual at time two. It's not correlated with time three. It's not correlated with time four. Now, this could be a problem because even though in the multi-level model we're accounting for the fact that observations are clustered within a person, we're not sort of saying that observations that are closer together in time are more similar than two observations that are farther apart. And we might absolutely believe that. There might be something that happens that affects, three observations, but not the fourth. Like maybe a conflict with a spouse or something like that. And what we could do is create parameters in our data set, or in our model, I should say, that allow the residuals that are closer together in time to be more strongly related than those that are farther apart. And so we call these autocorrelation structures. And so what we would do is we would estimate the relationship in correlation between residual 2 and residual 1. Okay, and in a typical AR1, what they call an autoregressive 1 error structure, then we would raise the value of that correlation to powers the farther away it gets. Right, so the difference, and so essentially what we do is, so if we compare the relationship, if we look at the relationship between residual 1 and residual 2, we find that there's a correlation there, okay? And now if we look at residual 3 and residual 1, that's 2 time units of difference. So then we raise the correlation to 2, we raise it to the power of 2, which will cause it to shrink. So if the correlation was 0.5 and we squared it, that would give us 0.25. And then when we compare observation 4 and observation 3, we raise it to the third power, okay, because that's the difference between time 4 and time 1. And then we can see that it's 0.5 raised to the third power, which shrinks it even further. And so essentially what we end up doing basically is shrinking the correlation exponentially to 0. The farther and farther out observations get from each other. So that, that was a big answer, but that was a big question. So I hope that's helpful.
Next question. How do we deal with missing values for the MLM data structure? For instance, some participants may not report diligently their cravings when prompted.
Yeah, that's a great question too. So typically in the multi-level framework, it's using maximum likelihood to estimate the models. And maximum likelihood has some beneficial assumptions about missing data. So it assumes instead of missing completely at random, your data only have to be missing at random, which means that they're either missing for reasons that are unpredictable or for reasons that are predictable by other variables in your model. So what that means is that if you adjust the estimates for variables that you believe are responsible for the missing, you can substantially reduce the bias in your data. The first thing that I would do before you do any of that stuff, though, is to calculate something called compliance and to look at compliance across time. And you may actually find that people are highly compliant at the beginning, but start becoming less compliant as time goes on. You have more and more missing data, or the responses on your variables change the longer that people are in the study. And so you could actually adjust for that, by including a time trend, et cetera. You can, and another thing that people are starting to do above and beyond that is to do something called pattern mixture modeling, where, and this isn't sort of in the flavor of what I was talking about, but you basically look at different patterns of missingness across individuals. And so some people might be highly compliant in the beginning of the study, but their compliance fades out as time goes on. Some people might be less compliant in the beginning, but start to sort of get better, or maybe you have others who have random dropout. And so what you do, and Don Hedeker has written a lot about this, is you sort of perform a mixture model where you identify different patterns of missing. And then once you identify those different patterns of missing, you put them in your model and you adjust for them. And you can actually see not only how different patterns of missing affect the outcome variable, but how they affect relationships with the outcome variable. So there are many ways to go about it, and it's a big question. If you want more detailed information, I would check the work of Craig Enders, who's done a lot of really great work in this area, and go from there.
Thanks. Please address uneven measurement points. Participants have a range of 35 to 48 points. And again, another question about missing data. We added that in there as well. Okay, so uneven measurement points. This is particularly, I think, of interest or particularly difficult when you're trying to model change and talk about it as within-person change. If people are not represented at all time points, you have to be sort of thoughtful about what exactly the overall trajectory is. So for example, if I'm looking at craving as it changes across weeks, so if I do craving across weeks, and this is the slope that I get in some sort of intervention, or this is my predicted trend, then maybe there are more people in this part of the study than there are here. And so my population is essentially shifted because of things like dropout. And so in this case, I have to be really careful about whether or not I say this whole thing is a within-person effect. Different parts of this will be within-person effects. But the whole thing in of itself, you might not expect to see that entirely play out within a person, because there might be a difference between who is sampled here and who is sampled here. The bigger issue that I want to get to, though, related to the uneven measurement points, is that multi-level models do tend to assume that the points of measurement are equally spaced. Okay, and this becomes particularly important if you start doing auto-regressive type models where time t-1 was predicting time t. In that case, the estimate that you're getting, it assumes applies to all t-1 to t intervals. Okay, and so by default, then it's assuming that those are equal in length. There are ways to adjust for that. You could actually moderate the effect by the distance in time between the two, between t-1 and t-2. So you actually calculate that as a separate variable and moderate your autoregressive effects by that. And it would tell you how does the lag one effect change based on the distance and time between the two observations. That's a simple approach to address this. Another more nuanced approach that's starting to gain some traction is continuous time modeling in a latent variable framework, which actually will account for the fact that you're not making this assumption that the observations are discrete in time, but that they represent a latent time continuum, and you're going to estimate the effect and how it changes at different points in time. Thank you. Question about partitioning the within between subject variance of the predictor. If one does not prepare the predictor in such a way, but instead a raw score is entered, in this example, raw score of negative affect, what is the interpretation of the coefficient? Is that coefficient even interpretable? A combination of within and between negative effect? Is that possible or appropriate to do?
This is a great question. So if you go back to the original Raudenbush and Break materials, they've gone so far as to call that an uninterpretable blend. So the question is, if I don't do any centering to my predictor, if I don't remove between person parts from within person parts, can I interpret the effect of just raw negative affect, for example, as a predictor? So the answer is that you can actually, I think you can interpret it, but you have to be careful about the interpretation. The truth is that it's blending between and within person information. So part of the reason you see an association is due to the fact that some people have higher average negative affect than others, and also due to the fact that negative affect is changing from one moment to the next within the same person. What you can do is disaggregate the effects. You can actually look for whether or not the effect at the within person level is the same as the effect for the between person level. So you can do that either through post-estimation contrast, where you compare the coefficient you got it between and the one you got it within. And if those are not significantly different, or if the difference between the two is not particularly great, you might just leave it uncentered. Okay, and so this gets to your question of whether or not it's appropriate. If there's no difference in the within person effect and the between person effect, then it doesn't matter what's driving it, right? Then you can just put in the raw variable, and the interpretation of that coefficient would be the same if you're talking about the between person effect or the within person effect. So it can be done. There are times when it is appropriate. As a matter of fact, I often do that if I have a variable that's a covariate and I'm not necessarily interested in interpreting between and within. I just want to adjust for it. In that case, I might just sort of put it in the model, not split it so that I can sort of save on degrees of freedom, but be able to say that I've accounted for it. And also, like I've said, if you've checked and the effects don't differ at between and within levels, then there's no real reason for you to separate it out.
Thanks. This is the last question that we have so far. So if anyone has any other questions, there'll be time, so go ahead and send it in now. Could you provide an example of how, why accounting for autocorrelation of error would be beneficial? Also, what might that look like in these models?
Okay. Can people see this? I can't tell.
It is write large and keep your lines thick. It can be seen, but it's not super clear. It's a little pixel.
All right. Okay. All right. So there are statistical reasons why you might do it, and then there are conceptual reasons that you might do it. So the question is really about autocorrelation of the residuals. So let's do this. So I've got a model at level 1. Let's say it's craving. Is predicted by negative mood. Okay, and there's my residual, I times t. And at level 2, the intercept, function of a grand intercept, plus that person's deviation from the grand intercept, and then the negative affect slope. Okay, so we've talked about these. So this is the deviation of the person intercept and the deviation of the person slope. And we set up a matrix where, okay, set up a matrix where we looked at, right, the variance of the random intercept, the variance of the random slope, and then the covariance between these two. Okay. So as I've mentioned in the model, we make this assumption typically that the residuals are unrelated. Okay. But I've also sort of talked about doing this autocorrelation where we let observations that are closer together in time within a person be more highly correlated than those that are farther apart. Now, statistically, why we might do this is that if we assume, so first of all, so the reason I went through all this just now, the random intercepts and the random slopes, so the random intercept primarily is what's telling the model that the outcome is sort of clustered or nested, okay? That observations within a person are more tightly correlated than those across two people. Okay. If we stop there, though, then the model is assuming that within a person, observations closer together are not more similar than those that are farther apart. And that is time-based clustering that we're just ignoring. If we ignore that kind of time-based clustering, it's possible that we will be cheating on our power, okay? So our standard errors will not reflect that kind of clustering, and we might be overpowered to detect within-person effects, okay? So we do better to account for the fact that some observations are going to be more tightly clustered the closer they are in time.
Those can't be seen.
These can't be seen,
The
okay.
bottom of your point, except.
Okay. Okay. So statistically, that's why, 'cause we're fighting against type 1 error, and we want to have a more realistic expectation of not only the clustering at the person level, but the clustering with time. A conceptual example where you might think about this kind of thing is, let's say you have an association between craving and negative mood, okay, and we can find that the effect of negative mood is significant. So the higher your negative mood, the higher your craving tends to be. And then the residual variance is residual variability in craving. Now, there might be certain time periods when something happens that causes your craving across a few different values to increase. It has nothing to do with negative affect. And we might think about it as a random shock, like maybe you get sick and that affects your craving, okay? And so it would sort of push the residual values during that time period either up or down compared to your average residual value, okay? And that would create a dependency because all three of them are sort of caused by the same thing. Maybe you get into a conflict. Maybe you get stressed out, and that stress only sort of manifests for 2 or 3 readings but goes away afterward. Okay, so that's a conceptual reason why we might do it, is that there are random shocks that sort of occur in our day-to-day lives that will get picked up by these residual terms. And if we don't account for that fact, it can cause statistical problems and it can mess with our inference. Now, with all that said, often when you fit these kinds of autocorrelation structures, things don't change that much. So this is a good question. It's an important question, but sometimes it doesn't have too much consequence.
I wonder how the standard error is being calculated for the, excuse me. I wonder how are the standard errors being calculated for the random effects in SAS? I am an R user, and I believe it only reports the variance estimates and not the significance tests for the random effects. Thanks.
Yeah, great question. So what it's doing in SAS is, so I showed you a Z table that uses sort of a large sample approximation of the normal distribution. So here's what it's doing. So if we think about the distribution of a variance, okay, so if we're doing random slopes, and we were able to do this over and over and over again in a simulation study, and we looked at the distribution of the variance for random slopes, we would see something that looks kind of like that, right? A skewed distribution. And what the Z-test for SAS is doing is it's a walled test that uses a large sample approximation and sort of looks at a normal distribution and the probabilities for a normal distribution overlaid on top of this true distribution. And so if your sample size is large, and large is of course a relative term, but typically about 250 to 300 clusters, so 250 to 300 individuals. The normal distribution will be closely approximated, usually by the true variance distribution. But if the sample size is really small, it starts to do a really bad job, okay? So it won't fit the distribution as well. So the use of the z-tests that I did in SAS are using this normal distribution, this large sample approximation, to generate z statistics and associated p-values. If you have a small sample, if you have 100 clusters, fewer than 100 clusters, I would recommend you don't do that. And instead, you look at the log likelihood of your model. So your models will give you something called a deviance. And in the output, that's a -2 log likelihood. And you would run a model with a random intercept only, and then a model with a random slope, and compare the deviance scores, okay? And it turns out that the difference of two deviance scores is distributed like a chi-square, which matches that variance distribution much better. So that's sort of the gold standard way to do it. The z-test approximation I was showing you was a shortcut, but the true way to get at this is the log likelihood comparison. So that's probably why R doesn't do it. And in SAS, you usually have to ask for it. So to their credit, they sort of take a similar approach, but I'm not aware of whether or not you could even get it in R.
Going back to the last question, and forgive me, I'm not sure when this came in, so I'm not sure which last question they mean.
Mm-hmm.
I wonder if there might be a useful research question embedded in the contextual effect, the difference in the between and within coefficients resulting from the uncentered model. Do you have thoughts on that?
Yeah. The contextual effect is the difference in the effect at the between level compared to the effect at the within level. Now, I don't do a lot of educational research or anything where the contextual effect, I believe, came about, and there's a lot of really interesting research on the contextual effect. But when I think about intensive longitudinal data, I have a difficult time interpreting the contextual effect. So for example, if we took the effect of negative affect at the between person level, and we compared it to the effect of negative affect at the within person level, the difference that we get is telling us the effect of being a high NA person adjusting for your high NA moments, right? So it's the effect of being a high, and if you think about stress, this stress makes it a little easier, I think. It would be the effect of being a high stress person adjusted for the fact that you have high stress days, right? Adjusted for your high stress days. And so, I think it's challenging to interpret in the ILD framework. And maybe it's just because I don't think about it too much and don't do it too much. But I think in the educational settings, you might be interested in sort of student level effects and then classroom level effects. And there may be there may be effects that truly do exist at the classroom level and that are driven by totally different things than what occurs at the student level. And I think, that's where the contextual effect has come about. And I'm sorry, I just don't do a lot of that kind of research. But I think that's where the contextual effect has been discussed the most. In ILD, I find it really tricky, but I have to think about that a little more. That's a great question.
Thanks. In the example you show, we see only one cluster level, the person level. What if we have more than one cluster level? And what's the difference between nested and crossed clusters in a model?
Okay, if you have more than one cluster level, so if you have hierarchically clustered levels, you could do a 3 or even higher level model. I've seen 4-level models published. But so one way of thinking about it could be that you have moments within days within people. You might also have something called a measurement burst design where you have, let's say, daily diary bursts nested within longitudinal assessments, nested within people. And then what you could do is just add, so you'll have an intercept that captures the mean for each person. Then you could also have an intercept that captures the mean for each measurement burst, okay? And then you'd have variability within each of the bursts. So that would set up your 3-level model. Now, cross-classified random effects, that's something that comes about. So in an example of this might be if you have patients going to doctors. All patients who go to the same doctor might be more similar than patients who go to different doctors, but the hierarchies are imperfect. Patients might go to more than one doctor, right? So usually when we do these sort of hierarchical models, they're sort of perfect hierarchies. You know, a moment belongs to a single day, and a single day belongs to a single person. That's not always true when you have different kinds of nested structures. So the doctor-patient one, I think, is a perfect example. And in that case, what you have to do is sort of add 2 different random intercepts to capture the different clusters. So you would sort of add an intercept for the doctors, and then if you have longitudinal data, an intercept for the patients, and they may be correlated with each other, right? In the perfect hierarchies, they're not correlated at all. In the imperfect hierarchies, they will be, but you'll just sort of add 2 variance components, allow them to be correlated, and that's typically how that's dealt with.
All right, and then related question here. What are your thoughts on using a 3-level model versus a 2-level model when we do an EMA study that has prompts nested within days, nested within people?
So it's a complicated question. First thing I usually ask is, are there a sufficient number of prompts at the day level, or I'm sorry, a sufficient number of prompts at the within day level and at the day level, for that matter, to be able to separate variance reliably? And I don't know of a rule of thumb right off the top of my head. I mean, I have to look into that and get back to you. But if there's a very small number of days, so for example, if you've measured somebody really intensively for 2 days, but you measured them many, many, many times a day, then I would say that the best way to account for any day level clustering might be to just put a fixed effect that predicts differences on day 1 from day 2, and then use the random effects to capture the between person variance versus the within person variance. Can you repeat the rest of the question for me? I'm sorry.
Sure. What are your thoughts on using a 3-level model versus a 2-level model when we do an EMA study that has prompts nested within days, nested within person?
Yeah. Okay. So the first thing you think about is how many prompts you have, how many days you have, and I might even sort of calculate variability at each level before I even go to modeling. So you can do all the centering that I showed you with your predictor variable and center around days, and then center days around people, and just sort of take a look at the variability. If the variabilities are close to 0 at the day level, then I would suggest that you do a 2-level structure. You might also, so that's the sort of the methodological way to approach it. Another way to approach it might be to think conceptually and to ask, are day-to-day effects of interest, and are they sort of a different process than you would expect in the within day effect? And so for the craving and negative affect one, maybe the day level effect is a totally different thing, and we might have reason to suspect that it is. That might be, sort of predicted by weekly cycles or workday versus weekend differences or something like that. And so it's a totally different causal process than the shifts in craving that occur within a day. So if you have conceptual or statistical reasons, I might advocate that you explore a 3-level model, provided you have enough days and a decent amount of variance. One thing about 3-level models that is challenging, though, is that they can be difficult to converge, and they can be very hard. And you have to sort of think conceptually about, if you ask for a random effect of the momentary relationship, do you want that random effect to vary only between people? Do you want it to vary between days? Do you want it to vary between days and between people? So it sort of creates this, it's a little bit more than adding just a single level. It creates a whole other set of research questions. But I think if you have very strong day level clustering, so a lot of day level variance, and you have conceptual reasons to go there, I think it's worth the complexity.
All right, thanks. After you partition the predictor into the between and within piece components, the variability of these predictors may be very different. Can you speak to how one would interpret a 1-unit change for each piece? Would you want to standardize each piece, for example, by dividing the standard deviation? And how does that affect your decision as to whether one can model the raw predictor if the estimates for the between and within predictors are similar for a 1-unit change, but the variance of the between and within piece predictors are very different?
Yeah, that's a really, really good question. Right. So standardizing in this area, I think if you talk to 5, 10 different people, you'll get 10 different answers on how to do it. Yeah, I think you are kind of making the assumption when you compare the contextual, when you look at the contextual effect, and you compare the difference in the within person effect and the between person effect, you're sort of making the assumption that 1-unit change means the same in both. So that's an excellent point. And so if you look at, if you partition your variables and you take a look and the variance is way different at the between level than it is at the within level, then that might be alarming. But conceptually, you might also think of it this way. So the between level effect is giving you a 1-unit difference in the means, right? And a within person effect is giving you a 1-unit difference in the scores. And so conceptually, those might be 2 very different things as well, and often are. So what I might do then is, after you create, and I haven't seen this published anywhere, but this would be an interesting sort of paper idea to explore. I might take your variables, your between person variable and your within person variable, and then standardize them as you suggested. And then sort of, say at the outset that you've standardized them so that you can make comparisons of the between person effect and the within person effect. Now, statistically, I think that's fine. Conceptually, you might run into some you might experience some heartburn with that if you think a 1-unit change in the means the same thing as a 1-unit change in the values. I think that depends on your conceptual question and the variable that you're looking at. But I think it's an important approach to take, and it's a good thing to check.
All right, that was all our questions. So on behalf of everyone, thanks a lot, Mike, and we'll get this video up for those of you who want to check back and chew on what he said. Thanks, everybody.
Thank you.